Okay, this is chapter 4, strong ground motion. Following the first three chapters, chapter 1 was introduction to earthquake, just general overview. Then chapter 2 was theory of vibration, trying to understand the vibration characteristic of single degree of freedoms and multi-degree of freedom systems. And chapter 3 was, we just finished it. It was about wave propagation in elastic media, how the waves travel, the way they travel in a bar or deep inside the earth in 3D condition. It's similar, and that helped us to derive the wave velocities. And we saw the characteristics, how they pass through interface layers. So chapter 4 is strong ground motion, especially once it arrives to the ground surface or near to the ground surface, to the bedrock. That's what we receive, that's what we record using our instruments. And that's the one we process and use it for our, designing our civil structures. So we have section 4.1, strong ground motion measurement. We will measure it using instruments. And then we'll see strong ground motion instrument arrays. Globally, we have uh, so many recording stations, even in the lakes, ground surface, all over thousands of measuring recording stations. We'll see those arrays. And strong ground motion processing. Whatever we record at the instrument recording location, we don't use it directly for design. We have to process it. There may be some errors because of instrument errors or undesired noises, noise coming from, maybe ocean wave, wind, or a vehicle passing by nearby. So they will introduce some additional waves. So we need to filter out those waves. Once we corrected that filtering process, we call it baseline correction. And once we process it, now it's going to be ready for especially designing our civil structures. And we will see the detail of what each motion look like. It has, ground motion parameter, it has amplitude, peak value, or the frequency content. Depending on the frequency content, is it a single frequency, multi-frequency, or where is the natural frequency, where is the peak value? That all helped us to see if our structures are in danger. And also we'll see the duration. Is it large duration? Is it, for seismic, it's common to have anywhere from 20 seconds to 2 minutes, 3 minutes, depending on the area. If it's a rock site, it's very short duration. If it's a soil site in a sense, deeper soil layer, it gets longer duration. And ground motion response spectra, this is the one you commonly see in designing. There is a plot with ground motion response spectra. We'll see how this plot is developed and how we use it for our design. This is also the one which is commonly input for our softwares. Whatever software you use, this is a common ground, the input value. And we'll see prediction of ground motion for design purpose. This is a wide area, how to predict the ground motion for a specific site, but we'll look at it like an overview. This is more what seismologists do. They try to predict. They try to identify the faults causing the earthquake, and they apply their attenuation equations, how it travels to the ground in the interior of the earth. And finally, they predict the value, the ground motion at the ground surface or at the bedrock level. Then that's our input in our case, but we'll briefly look at what they do. So the first section, strong ground motion measurement. The way we measure it, we briefly talked on chapter 1. We can use seismograph. That's analog way of recording it. We have, an instrument like a drum rotating continuously, and it's called a seismogram, where it has a paper where the pen is scratching on it. And this whole thing is fixed to, let's say, to the bedrock. And when the seismic comes, let's say in this direction, in the red arrow direction, then it shakes the whole instrument. It has a frame with a suspended mass. This heavy mass, it's designed not to move. We design this, whatever you see here, wire, we specifically design it not to move. It has a damping stiffness property within this wire. We specifically design it, whatever seismic motion comes, this mass doesn't move. But the other things are rigidly mounted to the bedrock, so they move. The drum move, then this pen scratches on the paper, and we get that recording. This is the old days analog way of recording the seismic, and it uses displacement of mass and can be very large in size. And because this is the old ways, but nowadays we use accelerometer. They are tiny, very small instruments. They measure accelerations of the ground. Once you get acceleration, we can integrate and get velocity and displacements. So digital accelerometers are very widely used nowadays, and they can sample from 200 to 1,000 data per second. So this is the most common way of recording earthquake nowadays compared to the analog, the old ways. So the design concept for vibration measuring instrument, the main design concept is the same. Remember what we studied in chapter 2, theory of vibration, and we had a wide coverage for 1 degree of freedom system. That concept is very applicable to the vibration measuring instruments. If you see all of them, you have a mass, you have a rope or wire, but that wire has stiffness and damping properties. We know that a vibration occurs, the framing, everything move, and this is relatively stable, doesn't move. So it makes a scratch, we get our seismogram. And this is for one direction. You can have this setup in 3 directions and get the output in 3 directions. All can produce this. And this can be digitized. Using transducers, electrical components, we can get analog data digitized and gets really uploaded to the network internet very quickly. So within the occurrence of an earthquake, within like 1 minute, 2 minutes, within the first 10 minutes, you may see data coming out and being published. The more data is obtained, they refine the data, they process it, but you can get records like that. So the main concept is it's a 1 degree of freedom system. You have a suspended mass, you have a stiffness and damper attached to it, which is designed not to make the mass move. So we have a ground moving, so ground displacement, ground acceleration, then the mass moving, the mass displacement of the mass, acceleration of the mass. This can happen in 3 directions for 1 degree of freedom system. Remember from our chapter 2, from the general equation of motion, especially for ground motion, we have this equation, which is the mass times acceleration of the mass, the damping times the velocity of the mass, which is a damping force, and the stiffness force, stiffness times displacement, equals to the inertial force, which is a mass times acceleration from the ground. Now, the solution of this equation, we saw that it has a non-dimensional form of, let's say, U by UG, the mass displacement by the ground displacement. It has this form. W is the forcing frequency from the seismic. Wn is a system frequency, the mass and the ground where it's attached, or the rope or the wire in this case. W by dN. So it's in the form of function of the frequency ratio. It's also a form of the damping ratio. Or in another form, the damage, it can be in the form of U by UG. UG dot dot. This is acceleration. The mass displacement by the ground acceleration can be given by this form. It's in the form of W, omega and omega n. I shouldn't say W, it should be omega, plus the damping ratio squared. And for more detail on this equation, you can look at chapter 2, what we discussed before, or you can look at this section, reference 1 of section 3.2, that's the Kramer book, or the Braja M. Das book, which is a reference to section 2.9, or reference 6, I believe this is Anil K. Chopra book, section 3.7. Now let's see how they design those instruments. If you see the plot of U by UG, this is a non-dimensional plot. And if we plot it over frequency ratio, and for different damping ratios, you'll get a chart like this. This is a plot of this equation. Now, look at carefully. There is some observation to make. Those are the ones which are being put into application. So if you see this, if Wn is designed to be small, omega by omega n, if we design omega n, the natural circular frequency of the mass and the spring, if we design it to be very small, then this ratio is going to be larger, right? We are talking in the larger area. So if W by, oh, sorry. If W by omega n is larger, which is larger than 2, this area, we are deliberately making the omega n small. Let's go up here. And if you consider, see the value of U by UG, the mass displacement by the ground displacement is about 1. For what? For a damping value of 0.7. So you see this, it's getting constant. For a damping value of about 0.7, and for with a frequency ratio of larger than 2, the U by UG remains constant, a value of 1. So if we select an instrument, purposely make the damping ratio of 0.7, and purposely we design our stiffness to be, this frequency ratio to be larger than 2, then we get whatever record we get on that instrument, the mass displacement is the same as the ground displacement. So displacement, so there is a drawback. This is like a displacement measuring instrument because we are getting a displacement. Whatever the instrument records as a displacement is the same as ground displacement. So you can have a displacement measuring instruments like that. So which means if it is designed like this, those analog records that you see on the scratch, on the seismogram, the peak value of the displacement is exactly the ground displacement. That's what it means. But there is a drawback. Displacement measuring sensor is inconvenient to manage because it has either large mass or soft spring or both. To make this large, omega n, you need large mass. To make this omega n small and the frequency larger than 2, you need large mass. So this mass, you see here the suspended mass, is going to get bigger. So that's a drawback. We don't want it too big. Or you need to play with a soft spring. We may have a stability issue. No matter how you design it, it's not that convenient. It's heavy. So it can be large inside because it must accommodate the anticipated support displacement. And in seismic case, the ground displacement can be very large. Sometimes it can reach to 3 feet, which means you need to have an instrument which can measure 3 feet over here. That's going to be big. This scratching is going to be 3 feet. So displacement measuring instruments, they are not popular because they have this drawback. They need to be bigger in size. Let's see acceleration measuring instruments or accelerometers, or they call it acceleration sensors. You'll find this commonly applied in many places for geotechnical, for hydrology, mechanical engineering, electrical engineering, in so many places. The design concept is from that solution of that equation, the general equation of motion, you can put it in this form, the displacement of the mass by the acceleration of the ground. You can have this form, 1 over this. Let's plot this. If you plot this for different damping ratio values, these are the charts you get. Now let's focus. Our purpose is to find some usable damping ratio. If Omega n is designed to be large. If you make this large, it's the denominator and makes the whole thing small, right? We're talking something like 0.4. If the frequency ratio is less than 0.4, we are in this range, right? Let's see, let's go up and see what's happening. If you see a damping value of around 70%, it remains again constant. So we are taking advantage of this property or this observation from this dynamic solution. So if we design our instrument to have a frequency ratio of less than 0.4, which means we have a control on omega n because it's a function of the stiffness and the mass of our instrument. We don't have a control on omega because this is a seismic part. But by designing like this for different value of omega, if we make it to work less than 0.4, we can achieve a constant value, or the ground, the mass displacement we see divided by the ground acceleration, it's constant. Actually, what it means is what we measure as displacement through our instrument is actually ground acceleration, if we design it this way. That's how accelerometers work. So a damping value of all those instruments, they use a damp value of around 0.7. So if it's accelerometer, then whatever you're measuring, it's a ground acceleration from this solution. So they pick up acceleration. Note that natural frequency of instrument is large for accelerometer design. Yes, omega n, we make it large to make things small. We're talking less than 0.4 frequency ratio. Omega n can be designed to be small using a small mass. For displacement measuring instrument, we were using large mass. Now we need only small mass or stiff spring. Because of this nature, modern accelerometers are very small in size and are preferred for practical application of vibration measurement. They are tiny. So this is a design concept they use. They make them really tiny because you need very small mass and stiff spring or split spring. If you design it that way, then the instrument you have is actually picking acceleration. Modern accelerometers, they can be different sizes. Some of them really, really tiny. This is one seismic measuring instrument, Seismic Network Earth Observatory of Singapore. I just picked it from Google. So you can see it's accelerometers and some batteries and things like that. And it has a wiring system because it's being digitized. So it records any motion and digitize it, and we use accelerometer. They are very small inside. It can be very tiny to any desired size. But inside, that's what they have. It's a spring mass system, but a tiny mass with a stiff spring. Other application of accelerometers, you may see them in different application. A motor vibration. When it operates, it has vibration. We want to make sure that it's not vibrating significantly. So this yellow portion you see, it's accelerometer attached to it. So we want to record the acceleration. Once you get acceleration, it's easy to get displacement and velocity of that mass vibrating. If there is excessive vibration in this motor, it can get damaged. So what we're doing is applying this sensor, accelerometer sensor, get the recording. If it exceeds a certain value, there is automatic shutdown. So this is instrumentation. It's automatically being monitored for its own safety. Or like a pump system with a smart vibration motor. You have a pump running, a generator running. Where I'm working right now, our generator, it produces electricity, but we don't want excessive vibration on it. So we are constantly monitoring it through using accelerometers. If it exceeds a certain value, it's shut down immediately. So we limit the damage on it. Or you can have a wide application of these accelerometers even in your smartphone. One application is when you rotate your phone from a vertical display to a horizontal display, that is being observed by the accelerometer inside. Accelerometer saying, hey, there is a change in orientation. So the image needs to be, changed. It doesn't stay vertical. It automatically makes it horizontal. Or accelerometers are being commonly used in smartwatches. They monitor your health movement. You're walking, you're running, you're cycling, sleeping, your blood pressure, anything. So there is a wide application of accelerometers. We're focusing on the seismic part, but there is a wide application. You'll see them in your daily life in the future. But the main understanding is just that's how they are designed. Section 4.2, strong ground motion instrument arrays. Now, if we know there is seismic, it occurs, it travels, comes to the ground, and we record it using accelerometers or the drum in the old days. To do that, there is a wide instrumentation array. There are different organizations with different recording organizations. The GSAN, that's good. The IRIS and USGS. IRIS is the Incorporated Research Institute of Seismology, and USGS is the United States Geological Society. The GSAN is those a global seismograph network. It had all these stars. I mean, by now it may be even much larger. This is from 2008. This is just to show you, where we have it, and we should put it in so many places to record. In chapter 1, we see an example when an earthquake occurring in the Atlantic Ocean, and recording station in Canada and Mexico and in France, they picked those motion. We made those circles and we identified it to be in the Atlantic Ocean. So to identify the location of an earthquake, we need to have instrument arrays globally distributed. We also saw in chapter 3, there are shadow zones. There is P-wave shadow zone, S-wave shadow zone. If an earthquake occurs at one place, some of these instruments, they don't pick it up because they are in the shadow zone. So there are different countries, Australia, Canada, France, Germany, Italy, Japan, US, and many others. I'm sure there are recording stations also in Ethiopia. Tingarakilo University, there must be one or nearby. So we have all this global network of instruments. When an earthquake occurs, it gets recorded in many of them, if not in all of them, and it gets refined. The error gets minimized. And strong ground motion processing, once you record it, it's common to have this kind of data recording. The data that you get, it has information, heading. For example, this data, it's acceleration record. Type of data is acceleration record. You use accelerometers, that's what you get. Acceleration record. Units, centimeter per second, centimeter square. Number of points, there are 2,000 points in this data. Sampling rate at every 0.02 second. So this data you see it's acceleration only. You don't see the time here. They give you only the duration. If you say the first one is recorded as 0.0, the next one is 0.02, next one is 0.04, it goes on like that. So it tells you many more information, the locations, where it's recorded, what type of instrument recorded it, everything. This is in 1989. I took this as a sample just to show you what it looks like. This is called a sample raw data. We didn't process it yet. We just recorded it. And it contains so many things. There can be noises. When this gets recorded, there may be a vehicle passing by nearby. There is a vibration caused by that vehicle, or even a wind blowing the trees. So it contains so many things to be refined, but this is a raw data. And you can get this kind of records online nowadays. You can get them for free. There is a large set of data. If you go to usgs.gov, United States Geological Society, or University of Michigan, and many other sites, you can use this website. They give you earthquake data from different recordings for free. And raw data obtained from strong motion instruments may include errors. It may have a background noise or instrumentation error. And when you plot the acceleration time, that 2000 data points we talked, you can briefly look at it. At times equal to 0, it starts 0.2. And at times 25, it has some value. You can clearly see that there is non-zero initial and final values. That's not what we want. When it starts, it must start from 0, unless something was occurring here. When it ends, we want it to be 0 also. It's over. So this shows you there is some noise, there is some error. It can be instrumentation error. So background noise is one kind of error. It's from different sources, such as traffic, construction activity nearby, ocean waves. If you have an instrument inside the ocean, because of the ocean wave, you can have some noise. Wind, trees, and building vibration is C, which can introduce non-seismic noise at both low and high frequencies. Background noise needs to be removed, so we need to filter it out. We need to process it somehow. We cannot use it directly as we find it. Or it can be also instrument errors, which may indicate the initial and final records not being 0, which needs correction. This is an example of raw data from El Centro earthquake raw data from Western US. So if there is an error in the data, it's dangerous. We need to correct it before we use it. Because we integrate acceleration. Our initial raw data is, let's say, it's acceleration. We integrate acceleration to get velocity. We integrate velocity to get displacement. If there is a data error in the acceleration, every time we integrate, the error is being magnified. So a small constant error due to the triggering acceleration initial value error, it will result in a linear error in velocity and a quadratic error in displacement because of the integration. As a result, direct integration of the recurrent earthquake without baseline correction can result in drift or velocity displacement time history plots. That's what you see here. You don't see that error in the acceleration in the initial value, in the initial recurrent. But when you integrate it and see the velocity, you can see how the velocity, the 0 line is right here. Your velocity plot is supposed to vibrate over the 0 line, but you see this drift. The 0 line is around here. The velocity plot is somehow going lower. And if you plot it, the displacement plot, it's even worse. It's like a one side, like a static displacement. Normally, what we have is during a seismic vibration, the displacement should also oscillate around the 0 line. We shouldn't have like a constantly. This is because of error. Or you can see this another example, the 2011 Christchurch earthquake. Acceleration is, you can see acceleration here, but you don't see the error. The solid line is the corrected one. We'll fill that out. The high frequency, the low frequencies outside the range of our interest, they should be filtered out. And there is also another plot, is T1 and T2, that's like a sample. They look on top of it. But when you see it in the velocity, you can clearly see the raw data with the dashed line and the corrected data with the blue line. You can see the difference coming out. The corrected data should be oscillating about the 0 line. It's more clear for displacement plot. A corrected displacement time history is oscillating about the zero line. But the one with the error, see where it is going. So before you use a seismic data, you need to integrate it. Usually you can find it when they those sources, when they provide you, they can provide you both acceleration, velocity, and displacement. You need to plot it and see if the data makes sense, especially in the displacement times 3 plot. If there is an error in the data, that's when we use a baseline correction. A baseline correction is basically filtering out the unneeded high frequency or lower frequencies. For civil structures, geotechnical applications, usually our interest is frequency in the range of 0.1 to 25 hertz mainly. But some sophisticated structures, like a nuclear power plant, we are forced to design up to even 50 hertz, 100 hertz. But you don't need frequencies beyond that. You don't need frequencies below here. Which means, so the earthquake is usually introducing frequencies in this range. If you have a frequency outside this range, that's error. That can be an instrument error, that can be a noise, a background noise. Like we said, such as ocean waves or a construction activity nearby. So we need to filter those frequencies. So we do baseline correction to make sure the initial and final acceleration velocity are zero. Before an earthquake occurs, there is no acceleration, it should be zero. There is no velocity, it should be zero. And initial value of displacement is also zero. So if you have non-zero values for the initial acceleration, initial velocity, initial displacement, it tells you something is wrong. So they should be zero. That can be corrected through a baseline correction. The second reason we do baseline correction is oscillation throughout the data is with respect to the zero line. About the zero line, we may have some permanent displacement, it may get little drift, but you cannot have a constant drift. Buildings oscillate about where they are. If it's a zero line, when the earthquake comes, buildings oscillate about their original position. If that's too dangerous, then they can get collapse. We're not talking about that. We're talking the elastic vibration. So it's about the zero line. So these are the two main reasons we do baseline correction. And the baseline correction is data filter or high frequency, low frequency filtering. A high pass filter, there are softwares doing this. So this is not going to be done by hand. A high pass filter removes all low frequencies. Anything below 0.1 hertz, we don't need. We remove it using high pass filter. Anything above 25 hertz, depending on the structure you're designing. Some structures, they don't need high frequency, 25 hertz. Some structures, 33 hertz, commonly taken as a rigid frequency. Or you may go up to 25 and 100 hertz, depending on how critical the structure is. Or you can use a band pass, which removes both high and low frequencies. There are free softwares, free programs for processing the strong ground motion recorders. USGS, United States Geological Society, has a program which is free for any user. It's called BAP, Basic Strong Motion Acceleration Processing. Or there is a widely known BiT-CEng. It's a commercial software, but they provide it for free for students. It has a limited version. It's very easy to use. It has very clear manuals to use. And BiT-CEng, it's, I think, a European company. It sells this SeismoSoft software, and BiT-CEng is processing the initial data. They do a lot more than that, but this is what we need. You can go to this website and get the free version of the software. Last year, I provided to the students, your senior students, get this because there is a project to do with this. You'll get raw data, you'll process it, and see the errors, remove the errors using this program. So this company, SeismoSoft, they provide for free for 1 month. So if you download it today from their website, you can get the software for a month and you can finish your homework. And there are many other sites. Many advanced programs have baseline correction implemented in them. You can use, MathCAD, MATLAB, and also even like FLAC, Plaxis, they may have it, but it may not be easy to understand. If you don't know FLAC or Plaxis, it may not be easy to understand what you're doing. But Sesmo Signal is specifically, you can use it for processing. It's easy. Ground motion parameters, section 4.4. There are 3 significant parameters to describe an earthquake ground motion. Let's say you have acceleration time history. We talk about the peak value, we call it amplitude. We talk about the duration. Is it 20 seconds? Is it 1 minute? How much is that? Because duration matters also. A large earthquake with a very small duration is not that significant compared to a smaller earthquake with a large duration. So duration matters. The peak value matters. And the frequency matters, frequency content. If you remember the story of resonance, we are dealing with frequency. If the frequency of the earthquake matching with the frequency of our structure, then you can have resonance. So we will check also how far we are from our resonance point. Are we close or are we far? So these 3 parameters they can describe the ground motion parameters: the duration, the amplitude, and the frequency. When we say amplitude parameter, it can be peak acceleration. We call it peak ground acceleration. That's the peak value. If the peak value in the acceleration time history recurred. If it's a horizontal recurred, it can be PGA, can be PHA, peak horizontal acceleration. If it's a vertical recurred, it's peak vertical acceleration. PGA is most widely used amplitude parameter. Usually for our designs, our softwares, our input is in terms of acceleration time history. There is a wide application. PGA is associated with high frequency ground motion. You can also get a record of peak velocity, or you can integrate it and get it, but we use it in rare cases when we design. It's an intermediate frequency. We use it for bridges, tall buildings, things like that. But most commonly, we use the high frequency, the peak acceleration. Peak ground velocity is just the peak value in the velocity time history plot. PGV is governed by intermediate frequency ground motion. It's often used instead of PJ if dealing with long period structures. And PGD is also peak ground displacement, the displacement time plot. The peak value is PGD, peak ground displacement. We don't often use PGD for design, except because it's a very low frequency parameter. And it's usually applicable if we are dealing with very long bridges or structures with very low frequency or very tall buildings. In that case, there is some application to it. Let's see some drawback of using amplitude parameter alone. We know that seismic parameter, ground motion parameters are 3: the peak value, the amplitude, the duration, and the frequency content. So when you select your time history for your analysis, you can have 2 motion. One has a larger peak compared to the other one, comparing input motion A and B. But this one has very less duration for the peak values compared to this one, larger duration. Assuming if the peak value of this larger, and if you use this acceleration time history for analysis, it may not have that significant impact on the structure compared to slightly lower value, but with a large duration. That's what all this is saying. Both records below A and B have same maximum amplitude, but B, figure B, this one, clearly has much more energy with several peaks over longer duration. So duration matters. regardless of how peak the acceleration is. Because the energy content in the end is the plot of this acceleration times 3 with time. If that area, if you go to each delta t and find the area, this one has less energy compared to this one. I took this figure from reference one, figure 3.12. You can see more detail over there. Or frequency content parameter. When we say frequency, in chapter 2 and 3, we have seen low frequency and high frequency. The frequency we are more interested is, let's say, while filtering, we're interested from 0.1 to 25 hertz. So the extreme values, we may not need it. Or we're not interested in a single frequency, let's say 10 hertz, or around here 16 hertz, or 25 hertz. If an earthquake comes with a single frequency, it's not that damaging. But if it contains wide variety of frequency, you see this spectral amplitude with frequency plot. We'll see how to get this plot from a time history plot, but see the frequency content. So an earthquake with a larger peak acceleration, but a narrow band of frequency is not that significant compared to slightly lower peak, but with a larger frequency content. They're wide. Because if it's narrow, it's going to damage buildings with this frequency, right, in this case. But if it's a wide, then any structure is being felt, anything around here. For example, if you come around here, a structure with this frequency, let's say this is 5 hertz, then the red plot with the narrow band is giving this much acceleration, maybe 0.5 g. But this wider one is getting this much acceleration. The larger the acceleration, the larger the force. So that's why it says lower amplitude, but over a broad range of frequency. So the larger the frequency content, the more damaging generally. So this may be a good point to stop the class. We'll continue next time. And we are in slide 21 versus, I think, about 40 slides. We'll finish it in the next class.